Hello, everybody. Welcome to today's current seminar. Today we have two talks, three speakers. The first two speakers are Juliette Vanderhaeghen and Júlia Vicens. They will be giving a talk on domain decomposition with Bayesian physics-informed neural networks. Juliette Vanderhaeghen started her PhD in 2023 at the UCLouvain in Belgium. Her research focuses on developing a digital twin capable of predicting how patients with breast cancer will respond to new adjuvant chemotherapy. To achieve this, she combines partial differential equations with deep learning techniques. And Júlia Vicens received a master's degree in biophysics from Barcelona University and a master's in artificial intelligence from International University of Rioja in 2024. She is currently a PhD student at Pompeu Fabra University in the Dynamical Biological Systems group. Her work breeds artificial intelligence, mathematical modeling, and biophysics to explore gene regulatory networks. This interdisciplinary approach led them to participate in a summer school on physics-informed neural network at KTH in Sweden, which serves as the foundation for the work being presented today. With that short introduction, the floor is yours and you can start your presentation.
Thank you. So, hi everyone. My name is Juliette, and today, together with Júlia, we are going to present you our work on domain decomposition with Bayesian physics-informed neural networks. So we started this project back in July while attending a summer school on PINNs, and that led us here. So let me now walk you through how the presentation is going to flow. Firstly, we are going to start with an introduction in which we'll define quickly the basic concepts of PINNs and BPINNs. This will enable us to highlight the motivation behind this work, and we'll then explain in a few lines how domain decomposition and CPINNs work. In the following section, we'll go into more detail about the methodology and the implementation of our methods. The implementation part will be illustrated by a case study. Next, we'll delve into the results of several different experiments, forward problem, inverse problem, and 2D space problem. In the final sections, we'll first do a quick analysis of the cost of performance of our method, and of course, we'll end by a conclusion. So let's start with physics-informed neural networks. PINNs are designed to solve partial differential equations by integrating physical laws governing them into the neural network training process. So as you know, there are two main types of problem. First, we have forward problem where the parameters of the PDE are known, and the objective is only to find a solution U. Then we have inverse problem, where certain parameters of the PDE are unknown, and they must thus be inferred from the data, along with finding the solution U. To resolve those problems, we define the residual function from the PDE, and this residual function is used in the computation of the loss to ensure that the neural network will respect the physics behind the PDE. In that way, the training is not only relying on data. So in more details, here is the general loss, which is composed of two terms. Firstly, we have one that accounts for data, and that is going to check that every observed data given to the model is effectively predicted. And in general, we have data for initial and boundary condition, but also we can use observed data across the whole domain. And so what is going to happen is that when we compute the loss, we are going to compare in each coordinate of the NU training data points if the prediction of the model matches the observed data. And the goal is to have that difference as little as possible. As we have a mean square error, we square the penalty. So the second part accounts for the physics and enforces the structure imposed by the PDE through the residual. We evaluate that residual in what we call collocation points. The collocation points are randomly chosen across the domain and are really dedicated to that residual evaluation. And once again, we want this mean square error to be as close to 0 as possible. So while we compute the loss and as we try to minimize it, the parameters of the model are going to adapt, and that's how the PIN is able to learn and approximate a function. So in summary, PINs exploit both observed data and physical constraints, providing a robust and interpretable approach to solve complex problems. However, while PINs can handle what we call epistemic uncertainty, they face some kind of struggle with aleatory uncertainty, which means they have difficulties with dealing with noisy data. But what do we mean exactly by epistemic and aleatoric uncertainties? So uncertainty in machine learning models generally falls into two categories, the epistemic uncertainty or aleatoric uncertainty. Epistemic uncertainty arises from model parameters and can reflect, for example, the lack of knowledge about the data. So this type of uncertainty can be reduced with more data or with improved training. For example, we see here that every part with more points will present a lower epistemic uncertainty compared to the part circled in purple. So PINs can handle epistemic uncertainty to some extent through approaches like deep ensemble methods, where we have multiple networks that are trained and then their predictions are averaged. On the other hand, aleatoric uncertainty originates from the inherent noise or variability in the data, such as measurement errors or stochastic phenomena. And as you can see here, when we are going to have points with a lot of noise and variability, the uncertainty around the predicted solution is going to increase. And this type of uncertainty is irreducible and cannot be addressed directly by the PINs. So this is where we can use Bayesian PIN in order to alleviate this challenge. Indeed, Bayesian physics-informed neural network extend the capabilities of PINs by adding a layer of probabilistic reasoning. So while PINs rely only on deterministic models, BPIN are going to assign what we call a prior probability distribution to the network's weights and biases. And then through the application of Bayes' theorem, BPINs estimate the posterior distributions for the model parameters. And this will allow for the effective quantification in the solution of both epistemic uncertainty and aleatoric uncertainty. So this posterior, circled in green, is composed on the numerator by two things. So first, we have the priors, which describe our beliefs about the parameters before seeing the data. And then we have the likelihoods. And the likelihoods are the tools we are going to use in order to guide the training process of our BPIN. Finally, at the denominator, we have what we call a marginalization term. And unfortunately, that term is usually intractable. So this is why, to estimate the posterior, BPIN is going to use sampling methods, such as the Hamiltonian Monte Carlo or also the variational inference, which are going to allow to approximate that posterior. And this sampling is, in fact, going to give us statistics from all the samples. The mean and the standard deviation are the one that are going to interest us, because this is what is going to allow us for the effective quantification in the solution of the aleatoric uncertainties. The problem is that by using those sampling approaches, the computational cost drastically increases because of the iterative process of it. So while BPINs are very useful to handle global uncertainty, this problem makes the efficient implementation of BPIN particularly important for large-scale problems. And indeed, dividing the domain into subdomains would reduce computational costs and would enable to have individual BPIN in those subdomains that we could train separately in parallel and then join them to have the full solution. So we have just seen that BPIN can solve the problem of global uncertainty by incorporating a way of quantifying aleatoric uncertainty in addition to the epistemic one. But BPIN still presents a scalability limitation that PIN also struggle with. So what could we do to resolve scalability? And the answer is lying in domain decomposition. So domain decomposition is a technique that is used to break down a large computational domain into a smaller, more manageable subdomains, which can then be solved in parallel and independently, then combined to obtain the solution to the full problem. And the big challenge with that decomposition is that we need to handle continuity at the interface between domains. So a lot of methods currently exist, and each of them has a way of handling the continuity differently. On top of that, they can have a different way of formulating the PIN itself, or even use different strategies to split the domain. For example, subdomain-based decomposition is consisting in dividing the domain into smaller but non-overlapping regions. On the other hand, overlapping domain decomposition is going to introduce a slight overlap between subdomains, allowing the exchange of information between the subdomains. So finally, we have a last example, which is multi-fidelity domain decomposition. And this one uses different levels of complexity in different subdomains, applying more detailed methods in regions which requires higher accuracy and coarser models elsewhere, etc. So we had to choose one method, and thanks to the advice of the teacher supervising us, we chose to use CPINNs. CPINNs is a domain decomposition method using the subdomain-based decomposition in order to reduce the complexity of large domain by solving it as smaller multi-scale problems. With CPIN, the interface continuity is handled by introducing key constraints into the loss. So the added interface loss is composed of two terms. One that is going to check for continuity of the flow, and the other one that checks matching of solution values at the interface. So these constraints added as extra terms in the loss help maintain smooth transition between subdomains, thus overcoming the challenges associated with domain decomposition. In summary, thanks to this introduction, you understand that our work is motivated by two things. Firstly, there are two types of uncertainties that may affect the solution of PIN, the epistemic and the aleatoric. So while epistemic uncertainty arises from the parameter of the model, they can be handled by approaches like deep ensemble methods. However, the aleatoric uncertainty comes from the used, possibly noisy data and needs to be approached differently. So currently, the best method to handle aleatoric uncertainty in PIN is Bayesian PIN. However, the second thing that motivates this work is that BPIN also faces limitation at a larger scale, just like PINs. Indeed, when we have problems with multiple dimension or large solution space, BPIN becomes more expensive because of the marginalization term, which in higher dimensions is also not tractable. This is why the concern at the moment is that there is a lack of methods which allow to handle aleatoric uncertainty for large-scale problems. However, this will be of great value in cases where subdomain experience different level of noise, which in real applications can correspond to situation where, for example, we have experimental data in one port of the domain, and in the ports we have, for example, data coming from numerical simulations. Thus, to be able to address those changes, the idea of this work is to combine BPINs with domain decomposition, and in particular here, CPINs, to form our method. So introduction is now over. Now that we all understand why this work is being done and what are the concepts at the basis of it, we can move on to our actual method, how it is formulated and implemented. So in this slide, I'll go over the formulation of the likelihoods we are using for our method. So we first begin with the first two. So the first one, we have the data likelihood for observed data. And what is done is that we check if the predicted value of the solution follow a Gaussian distribution centered around the actual data with some variance sigma squared. So we want to maximize those likelihoods because they represent the probability to observe the data given the parameters. So we could also see that as minimizing the mean square error of our model's prediction and the observed data. Following the same principle, we have the residual likelihood for the constraints from the PDE. And we enforce that our solution satisfies the governing equation. Then we had some likelihoods for initial and boundary data. So the initial condition defines the state at the system at t equals 0, and we impose that our model should align with the given initial values. This is the same for boundary condition. A priori, XBC will be fixed to a value corresponding to the position of the boundary. So we check every data in time at XBC equal -1, for example, or equal 1. Finally, the contribution of this work is to add the last two terms, which account for the interface likelihoods. Indeed, we need to define something that is going to ensure the continuity of solution values and flow at interface. And once again, we use a Gaussian distribution to check for a deviation of the flow or the solution values. And these should be, in fact, equal at interfaces. So I'll now let Julia take the leads.
Okay, so to implement our methods and check the stability of domain decomposition with BPINs, we will train two different BPINs in each domain. So we are going to have a likelihood with three different terms, two of them that will depend only on the points of each domain and its respective parameters of each BPIN. And then a third term that involves both domains just at the interface. So to make it more understandable, we will illustrate our procedures and methodology using a Kahn equation that is just a diffusion reaction equation. We'll predict our concentration U. For inverse problem, we'll recover D, our diffusion constant. And we have also here our source term. Okay, so let's begin by explaining how BPIN is going to behave in that context, because that will allow us to make comparisons when we'll apply domain decomposition. We are going to have two principal kind of experiments, one that is more physical driven. So we are going to provide initial and boundary points that are the black crosses, and we'll add residual or collocation points where we'll evaluate the PDE, that are the red crosses. Then we'll go to a more data-driven approach when we'll still have the collocation points, but we'll remove the initial and boundary conditions, and we inform by data points. So in the first scenario, the model is constrained because of lack of explicit data. So we have a really wide uncertainty, epistemic uncertainty, that is represented in blue light. and is 2 times the standard deviation of the prediction. Then when we go to the data-driven approach, we can see that data uncertainty decreases, but at the boundaries is still a bit big because those points has less information about the neighborhood than those in the bulk. So now we split the domains, so we need to take a sample of points where we are going to check that continuity. Then we'll be able also to add some data points just to the interface to make sure the uncertainty at the interface is going to decrease. And also because maybe we have a grid of sensors and we are interested in recovered information in the area. So here we have a first example of how B-PINNs performance with domain decomposition. We have the first case with more physical-driven approach, and we have a very similar behavior as B-PINN in a single domain. When we add data to the interface, we can see that the uncertainty is decreasing as we have expected, but the uncertainty in the rest of the domain is more or less equal to the previous case. When we add the data, the uncertainty decreases. What we can observe is for T more or less near zero, we have a very wide uncertainty. This is because if we look at the sample taken to make sure the continuity is fulfilled, we can find a lack of points in T near zero. So that allows us to have a first sight that we can do domain decompositions with Bayesian PINNs without any problem, always that we allow enough points to check the continuity condition. So now that we are in context, we'll jump to our results. We are going to first show some examples of forward problem, and then we'll study the noise, adding different noises in each domain and same noise in both. Then we'll also change the size of the subdomains, and all those cases we'll compare with B-PINN in just one domain. Then we'll go to inverse problem, and finally we'll extend the 1D problem to 2D problem. So here we have a Fisher-PPE equation that is just a diffusion equation with a logistic growth. We can see more or less the same behavior, but now we have a bit more of uncertainty on the sides because it's where we have a faster dynamics. If we move now to Fokker-Planck equation, just the diffusive equation, we find the same effect, but now at the interface because it's where we have now the faster dynamics. But we can solve it adding some data points. If we study an hyperbolic equation like Burgers that has a shock and we set our interface just at the shock, we can see that the physical approach is not as well as before, but it can also fix when we add data, or as we'll see later, adding more collocation points. So now we have to take into account that when we take measurements and we add data, we always have noise. So we have to know also how our method is going to handle aleatoric uncertainty. We have here some examples of the levels of noise we are going to work with and how it affects to the measurements of the short term. Here we have the first results with noisy measurements to the more physical-driven approach for one domain and the decomposition. We can see more or less the same behavior, and up to 10%, the accuracy is quite well, but then it's going to lose that accuracy because of the noise. We can also now add the data at the interface and check that at 10%, that is actually quite big level of noise, it's still performing well and it decreases the uncertainty at the interface, but the rest of the domains is still performing as the case before. Nevertheless, at 15%, it starts to perform more abrupt and with more perturbations because it started to overfit the noise. If we go to the more data-driven approach, we can see more or less the same behavior as we can see in the interface. As more noise I have, more overfitted is my B pin, but in both with a split domain and with a single one. If we quantify that uncertainty, we can see that the absolute error is more or less the same in B pin and our method, and same for the uncertainty. So actually we can split domains without losing accuracy and without an increase of uncertainty while handling noise. We have here another example. Here we have Fokker-Planck, and we can check that if indeed we increase the number of collocation points, our performance is going to be much better even for burgers with the interface at the shock and with a 15% of noise, that it's quite high. So now maybe we are in a situation that we have some sensors and in some area they start to recall very high levels of noises, or maybe they broke and we have a totally lack of information and we want to combine numerical simulations with data and have a heterogeneity with the data. So it's important that our model can also handle that kind of heterogeneity. We have here a domain in blue without noise and a second one with noise. Just is the more physical driven approach, and we can see more or less the same behavior as before, what is a good news. And when we go to the more data-driven approach, exactly the same as before. But the good news is also that the domain without noise is not being affected because of the noise of the other domain. So again, we can handle with that kind of heterogeneity. If we measure that uncertainty and that accuracy, we can see again that B pin in a single domain and with domain decomposition is performing more or less the same. We finally are going to check what is happening when we split the domain in different sizes. We have here same size of the domains, and here the different ones. We can see that for those domains that are a bit bigger, the noise is impacting a bit more. So that also provides us that also makes us to continue with domain decompositions to be able to split the domains when they are so much bigger. Now we are going to add noise just one part of the domains that we have indicated here, and we have still the same results. So again, we can split the domains with different levels of noises, with different levels of sizes, and we can handle all the input.
Okay, so to put back the context, we just finished to see the results concerning the forward problem and its different experiments. So naturally, we are going now to analyze results obtained for the inverse problem. As you still know, inverse problems are problems where one or some of the parameters of the PDE are unknown and need to be inferred from the data. So what we do here is that we have the same residual likelihoods as for forward problem, but we add a parameter lambda1 and lambda2, circled in purple and green, that will ensure that the model we train while trying also to estimate those unknown parameters. So for our case study, we again take Vanderhaeghen equation. So as a reminder, in this equation, we have the presence of a diffusion coefficient D, which here becomes an unknown parameter. To find it using our method, we use 150 residual points, as well as 150 training data points in each subdomain. And in addition to these points, we add another 50 points, another 50 collocation points at the boundary between the two domains. We are going to compare with BPIN, and in BPIN, we thus use the same amount of points, but as we don't have an interface anymore, we don't have the 50 collocation point at that place. So in the plot here, you can observe three sets of points. The dark blue ones show results of the prediction of D in the first part of the domain, and the light blue ones show the prediction of D in the second part of the domain. The orange points are them associated to the coefficient predicted by BPIN. And finally, the black line represents the real value of the diffusion coefficient we are trying to find, which is equal to 0.01 in that case. On the x-axis, you can observe the evolution of the noise level that is added to the data. And quite logically, we can spot a tendency to predict values further from the real one as the noise level increases. We also observe some discrepancy between prediction of D in the first part and in the second part of the domain. This could be explained by the different evolution of the function on either side of the interface. And on the other hand, predictions using BPIN seem to be closer to reality, maybe because the estimation of the coefficient can be smoothed out on the entire domain. So to improve results, we decided to add some more constraints in the likelihoods in order to analyze their benefits. So we first tried with soft constraints, where we imposed that both lambda1 and lambda2 should tend to be equal. However, lambdas are still estimated through the two different residual likelihoods and are thus different in the two domains. Then we figured we would try harder constraints. So instead of having one parameter per domain, we only define one that is trained and that is learned to both BPINs. So already by those two graphs, we can tell that hard constraints allow not only better results than with soft constraints, but also to have much more similar results with BPIN than before. Here is a more detailed error plot of the predicted D compared to its real value. We can see that scores done by our method in blue without any adaptation is not doing very great and are impacted a lot by the noise. Adding the soft constraints in green have a small improvement and is still quite a lot impacted by the noise. However, we directly see that adding hard constraint is very interesting because the performances are a lot more better and can even compare to BPINs in orange. Here, you can observe a comparison between our method and BPIN with a level of noise in data equal to 15%. The performances seem to be quite equivalent between the two, and the function is relatively well recovered, given the present amount of noise and given the fact that there is a parameter we don't know. Here is another example with this time Fokker-Planck equation, where once again, it's the diffusion coefficient we are trying to find. And here you only have information for hard constraint because it was the most interesting to show, but the conclusions are quite the same as for Al and Can, even though here the function will be easier to recapitulate because simpler. Okay, so we have arrived to the last experiment. Our goal here is to show you performances of our method in 2D. Here is the setup of the 2D space problem. So we are going to use the same architecture as in 1D, except for the input and output dimensions of the model, because we now have 3 dimensions with time. The points are taken randomly in the space and time domain. And on the right figure, you can see an example of how the residual points are distributed across the 2 domains. You can observe here the results of our method in the 2D space domain. So we have here a section taken at time t equals 0. The orange crosses symbolize the residual points, and the black crosses symbolize the data given at the boundary and the collocation point taken at the interface. So we see here that the continuity is not handled perfectly, but it's also because we have not that much points where we check that continuity. But as time goes by, it's getting better. Also because we have more collocation point at that interface. This discrepancy at time t equals 0 can also be explained by what we said earlier about the faster dynamics. Now, here you can observe the 3D animations. On the left, we have the reference solution, and on the right, what was predicted by our method. We spot the same thing as shown in the section in 2D at t equals 0, with a little discrepancy between the two domains. But it's behaving quite well. To end this section, we would like just to mention that here we only have 3 different time points because of resources limitations. But with a GPU, it should be able to process more information. I will now let Júlia end the presentation.
Okay, so finally, we are going to talk about the cost of performance, and we'll end with the conclusions. We have plotted here the time required to recover D for each case, B pin in orange, in blue our method without constrictions for D, in green with soft conditions, and in purple with hard conditions. The results show us that B pins is more efficient in terms of time, while soft conditions requires an extra term for computation. So, considering computational cost, our method is more expensive because it requires a B pin for each domain. However, as problem becomes more complex, we hope that we are going to need a simple B pin for each subdomain if we compare with the complexity a single B pin needs to predict all the domain. And we hope it will help us to reduce the gap in the performance. Additionally, previous studies have shown that splitting the domain can accelerate computations through parallelization. So that suggests us that we can also parallelize our domains to improve our performance. So to sum up, we have proposed a framework that works well using Bayesian PINNs with domain decomposition, specifically conservative PINNs. And it also gives us consistent results for different equations, including hyperbolic equations like Burgers. We have achieved good accuracy, even with really high levels of noises, with both forward and inverse problem, with same sizes of domains, different sizes, same levels of noises, different noises. We have also tested the scalability to 2D problem. So our next step then is to parallelize the computation that will promise us a promising results. So thank you for your attention. Thank you for the opportunity of present our work, and we'll be very happy to answer your questions and suggestions.
Thank you so much for your great talk. Now we open the floor for questions. Do we have any? I can see Professor Sokumar, you have your microphone on, right?
Yeah.
Yes.
Thanks for the talk. This is Suku here. So from Davis, I had a question on, you had mentioned, both of you, that the importance of hard constraints versus soft constraints. So at the interface, so you're talking about the interface, right? Where you want to have more points or not, right? So did you just do a study in like one dimension to investigate this? Because in one dimension, everything is easier, right? So you can just divide the domains, and depending on the number of domains. And so would it be beneficial in general for to have hard constraints imposed a priori so that you don't have to worry about the interface? But of course, there are caveats to that you could have, you're constraining the neural network in some sense because you're enforcing continuity automatically, right? So I was just wondering about it, right? I don't know the answer myself, but.
We have also checked for 1D problem, like all the kind of experiment because of because we don't have so much power computation, but for
Yeah.
sure in 2D should be more complicated. But hard conditions can help us, but maybe we are interested in measure the inverse problem, like allowing the system having a smooth changes in space is more benefit, but the cost of computation is higher. So at the end, we neither know. We need to check all those experiments in a more large scale in 2D problems, but for that we need more computational power and the ability of parallelization.
Okay.
Thank you. Jacob, yeah.
Hi.
Can you first
Thanks for.
introduce yourself?
I'm a PhD student at Carnegie Mellon University, and I'm interested in physics from learning in general. And I have a quick question. So, in terms of the motivation, the reason that you consider a domain decomposition is that you're trying to parallelize the computation of the physics from learning process, or actually by doing the domain decomposition, you're actually able to obtain better accuracy because you kind of consider subdomains subsequently, or any clarification on that?
I mean, the goal of doing those subdomains is really to have B-pins that are going to be independently trained, so they also can be like more specific to the area we are trying to model. And with parallelization, it's like yeah, I mean, it's easier in that way, right? Like
Yeah, I can think of the parallelization part of the work, which say you can train multiple neural networks together at once, and then you can combine them together to save training time. And in terms of training subdomains separately, my follow-up question would be, what is the difference between a standard B-pins together with some when you decompose the domains, you add some additional loss functions between domains, or like in your previous slides, you have like additional data points on the boundary of the domains. Like, what would be the difference between that kind of neural network and your neural network?
I mean, at the end, like if you train without parallelization, in terms of accuracy, we have shown that it's more or less the same. So that's the benefit, that we can split it actually. So we are going to scale it to a large domain problems, and we are going to handle aleatoric uncertainty without losing accuracy. Because the thing is, we have not right now a tool to handle aleatoric uncertainty in really large domains. B-pins is good, but for large domain, it's really time required. So if we want to parallelize that, we want to speed up, we need a domain decomposition. So that is just like, okay, it's going to work. It's like we have enough information to just check the parallelization is going to speed our procedure enough to work with BPs efficiently for large domain.
Yeah,
Gotcha. So
yeah, because like the marginalization term that we have, like when we are trying to estimate the posterior, like with large scale problems, it's going to be more and more and more expensive because we have to sample, and this is why the domain decomposition is important.
Gotcha, guys. So basically, it's the computation issue on like a large domain for the PDE. Gotcha. So that makes sense, because I observed that also, to compare with B-pins, it seems that B-pin performs like relatively similar to your method, or I assume that it should take a lot more time for training, especially when you have the parallelization with your method, I guess.
Yes, sampling will require more resources.
So one last question would be, would you consider B-pins as a baseline that you can, or like a, I would say baseline is some like performance index that you want to compare with, say, is your goal to achieve similar performance with B-pins through this domain decomposition, or your goal is to actually achieve better accuracy?
No, it's not like better accuracy right now. It's like at least the same one to be able to speed up and further take a better performance in terms of time.
Gotcha. So similar performance, but better speed up with the parallelization through domain
It's to be
decomposition.
able, it's to be able to scale the problems and really
Gotcha.
able to handle like more real case problems.
Thank you. That makes sense. Thank you. That's all my questions.
You're welcome.
You okay? Do we have any other question? Yeah, Young-Q.
I am Young-Q from Brown. I have a just simple question. You just test your domain decomposition method for just 2 domain cases, but actually the main problem of the domain decomposition usually comes from the many subdomains. But let's think about the 1D case. If we decompose domain into 3 domains, 3 subdomains, then the middle, if we focus on the middle of the subdomain, then we don't have any boundary conditions. We just really that domain really depends on the interface condition. So I'm just curious, your interface condition is good enough to train that domains?
I mean, I think that the focus here it's more go to the more data-driven approach, because at the end, what you are interested is in the aleatoric uncertainty. So you are going to have also data like that is going to guide you. You are not only with the boundary conditions, you also have data.
But even if we have a data, because we cannot, okay, then even if we decompose the domain, we already have many datas. You don't use the only physics informed laws.
Yeah, I mean, if we only use PDE and boundary conditions, I guess that we are going to handle with more epistemic uncertainty. But at the end, pins can handle it. The thing is, they cannot handle aleatoric one. So at the end, when you add data, I guess that problem is going to vanish.
See, because in classical domain decomposition method, if we decompose more than 2 subdomains, then there must be the blocking subdomains, the middle part of subdomains. To resolve that problem, we usually add the force structure. So we usually propose the 2-level domain decomposition method to handle that kind of problem. Then we can get the algorithmically scalable the method. So maybe. So I just curious that even if we decompose more than 3 or 4 subdomains, if the performance is preserved, then it's fine. But if not, then maybe you need the force space, force problems.
Yeah, maybe it's something that we should check, but we have to work in more domains.
Okay, thank you.
I have one more question. This is a follow-up question. Suku here again. So just going back to what you were saying before, I mean, is there a way to, if you look at aleatoric uncertainty, is there a way to measure that when you have, say, 2 methods, right? So you're using 2 methods to solve the same problem, and I want to only focus which is worse on capturing aleatoric uncertainty. So how would one go about that?
Like just aleatoric uncertainty
Yeah,
between
because,
a pin with 1 domain and a B pin in 2 domains.
Right. How do you just compare it, or even just some other method, not even pins, right? If you just want to assess if a method is good, like you were saying before the introduction, right? It's good for epistemic uncertainty, but not for aleatoric uncertainty, right? So then you say, okay, now what do I do? But how do you assess just that component, so that to discern basically whether a method is suitable and better to draw some inferences from just that part, right?
Yeah.
I don't know if the question makes sense, but
But here, actually, we already know that BPIN can handle that aleatoric uncertainty well. And so
Okay.
really here, the goal is really just to be able to scale that capacity of BPIN to handle that aleatoric uncertainty. Because for now, we lack of methods to do that.
Okay. So it doesn't matter that, in pins or otherwise, there are other issues of training errors and all that. That's independent of that, right?
Can you repeat? Sorry.
Because when you're doing an optimization problem which is nonlinear and non-convex, the solution you get is not the best, of course, in general, right? So there is uncertainty there also, right? It may give you a local minima somewhere which is non-optimal or very far from optimal, right? And you have to just go with that because it's hard to, that's what the trainer, the Adam or whatever you're using gives, right? So that's what I'm thinking.
Yeah, we're just using that method and we are trying to scale it.
Okay, thanks.
Thank you. Do we have any other questions from the audience?
Maybe, hi, my name is Juan and I'm a PhD student here with George. Maybe answering part of Suku's question, like some people have tried using the negative log likelihood. That's another way that you can infer like the aleatoric uncertainty. And actually, there are some approaches that they have adapted that to pings, and it's a bit more straightforward because you only would have like one additional output of your network, and that network would essentially tell you what is the aleatoric uncertainty. And that method was not developed only like basically for neural networks, for training neural networks. It was developed for like classical machine learning methods, and it was like based on some of the assumptions that Juliette and Julia were explaining. But when then that brings to my question, it was like, hey, Juliette and Julia, did you try, because right now you said that you're addressing this problem because is the only way, using B-pings is the only way to deal with the aleatoric uncertainty, and that pings cannot handle aleatoric uncertainty. But did you try some of the approaches? For example, there's a new paper by Songren from our group. Like, I don't know if I can put it in the chat. It's somewhere around here. And they did something like also with pings for it's recent. It's like maybe 1 month ago, I think it was published. And also let me see, where is the other one? Yeah, so did you try anything like that, or what? Well, because I'm a bit confused about the term that the B-pings are the only way to deal with aleatoric uncertainty. It sounded like a bit too strong for it was like a really strong claim.
No, I mean, I don't know all the methods. It's likely that it's going to be more of them, but we focus on that because we found that they have a lack on large scales, and we only want to allow B-pins to perform also in a large scales.
Yeah, so we don't think it's the only approach, but we know that it is a good approach. So this is just why we focused on that, but we didn't try other methods.
Yeah, but and then it goes like maybe it would be a good idea to somehow compare with the other method to see how to see how well they are. And also, did you, I think that I saw it, but just to confirm, you confirmed that your uncertainty predictions were covering the data, right?
What do you mean?
Yeah, like when you make your prediction, you get like some kind of let's call it like analogous of a mean field plus some type of perturbation, and that perturbation will be your uncertainty, right? And then your claim is that, well, not your claim, the general claim about this thing is like, ideally your error, the pointwise error should be somehow covered by that uncertainty range, which sometimes it's true, but well, that is going to a bit more into confidence intervals. But in that case, the question was like, did you do some analysis on the confidence intervals of your method?
No, we didn't were aware of it, but we'll check it and we'll take into account because we didn't thought about it.
Oh, okay.
Thank
No,
you.
but generally it was really good idea, really good approach, and you made like a really good connection between everything. So thank you so much for sharing this with us.
Thank you.
Thank you.
Do we have any other questions? Okay. I don't think so. So thank you for your great presentation. And I think now it's time to move on to our second session. Thank you, Julia. Thank you, Juliette.
Thank you.
Patrick, are you here?
Hello. Yes.
Thank
Huzzah.
you.
Oh, well, third time lucky.
Okay. Yeah. Okay. Our second speaker is Patrick Kidger. He will be giving a talk on an introduction to the JAX Scientific Ecosystem. Patrick is the tech lead on machine learning for protein optimization at Cradle.bio and founded much of the open source scientific JAX ecosystem. He has previously worked as a machine learning researcher at UCLouvain, held a visiting appointment at Imperial College London, and received a PhD from Oxford on neural differential equations. With that short introduction, the floor is yours and you can start your presentation.
Cool. All right. So hello, everyone. It's great to be here. So indeed, I'm going to say a few things about JAX. And I guess the only other thing I'll say before I crack on is that my presentation today is fairly short, I think probably 30 to 40 minutes. So I encourage absolutely everyone to just jump in and ask questions if you have them as we go through. So with that, here we go. So first of all, the way I'm laying out my presentation today is part one, just a quick recap of JAX, because I don't want to assume that people are necessarily familiar with this, although I'm guessing probably everyone has heard of it. Part two, I'm going to say something about JAX for deep learning, and then part three, which I think is probably in many respects the sort of the interest of a lot of this audience, is JAX for scientific modeling. And I think increasingly what we see these days is how deep learning techniques and scientific modeling techniques are just kind of the same thing. It's all a big auto-differentiable computation graph, whether it's neural networks or differential equations. And so my goal is to try and blend these three things together fairly smoothly as we go through. So part one, just a JAX recap for those who haven't seen it. And for those who have, I've only got one slide, don't worry too much. So what is JAX? JAX is essentially it's a NumPy-like Python library. And so you're used to doing import NumPy as NP and then NP dot whatever. Those correspondingly import JAX.NumPy as JNP, and then again you have JNP dot essentially the entire NumPy API that you're probably already familiar with. So I've got this fairly straightforward example here where we're just using this one particular operation. It's very simple. This is just NumPy.sum, JAX.NumPy.sum. And you can see that the function that I've written down here is how to compute the loss of a particular model given a piece of data X. So we evaluate our model on our data X, we compute this loss, this is L2 loss against our Y, and we return it. So this should hopefully feel just like NumPy, like normal. But then the thing this is the thing which I think makes JAX is its ability to compose transformations, to do these function to function or graph to graph, if you like, transformations. And so that often looks something like this. And so in what I've done here, I've taken this function compute loss and I've added this decorator JAX.grad. And in doing so, I've now got a new function, which instead of computing the loss, model and X and Y go in, loss comes out. Then with JAX.grad, what I now have is a function where model and X and Y go in, and the gradients of the loss with respect to the first argument, that is to say, the parameters of the model, that gradient, dloss, dparameters, is now what comes out of JAX.grad, of compute loss. And then in this case, I've actually gone and stacked another program transformation on top of it. This is JAX.jit. And this is essentially a fairly straightforward, please take the function that I'm given and then compile it down and make it fast. And as a result, this actually removes Python entirely after that tracing and compilation has happened. And so this is super useful for making things run very, very fast. That is going to be very important to us later, actually, as compared to, I don't know, like let's say PyTorch, where a lot of PyTorch work is often still using the Python interpreter, that really slows things down, in particular for things like differential equation solves, which have lots of little nitty components. To be clear, I don't bash on PyTorch too much. I use PyTorch every day. It's still great for other things. Then, okay, run anywhere. This is kind of old hat these days, right? We all run code on CPUs or GPUs or whatever. So yeah, this is true here as well. So in this case, maybe I say, let's go ahead and call this function. And now if I want to run this on my cluster of 32 GPUs, I can just put in these 2 lines. My model and my data will move over to these GPUs, split across them in a distributed fashion if required. And then the exact same function works in exactly the same way. So this is very, very easy to do. And so this is sometimes called auto-parallelism. And now, finally, we get to the point which I think is really the focus of today's talk, which is the ecosystem, all of the things that are built on top of JAX. Because JAX itself is giving you these sort of operations, these primitives, things like addition, multiplication, exponentiation, you know, all this usual jazz. And then it also gives you these transforms. And then on top of that, you have to go out and build things like neural networks and differential equations. And that is really where the JAX ecosystem comes into play. And so then finally, this is the final snippet that we'll add to this piece of code, where in particular Equinox is one of these libraries we'll see a little bit later, which is useful for defining models, or more generally to sort of put on my mathematical hat to define parameterized functions. So I define a parameterized function, a neural network would be a classical example, and then given this model, I can now just go ahead and run this whole thing. So this is the purpose of today's talk. With that, let's move on to part 2, deep learning. And I will again also remind everyone, please jump in if you have questions. In particular, don't let me confuse anyone who hasn't seen JAX before.
So Patrick, this is Suko here. I had a question going back. So essentially, you're saying that model can be any system, basically. You can define your own model and run basically this through it, right?
Yeah. Any
a
function is the way I would describe it.
Yeah. Okay. So you can just define that and then use whatever is already in JAX, essentially. Okay. Okay. Thanks.
Cool. Any other questions? I don't think so. Okay. We're going to see a very explicit example of what Equinox module looks like coming up. So let's take a look at that. So Equinox. So as I say, this is for representing parameterized functions. Neural networks are obviously this like big, you know, case that we see a lot of these days. It's neural network this and neural network that. But actually, examples of parameterized functions are absolutely everywhere. So this includes things like a differential equation solver, parameterized by its butcher tableau or something like that. This is very common. So let's go ahead, import this sort of usual collection of things, and then let's do it the simplest possible parameterized layer. So that's a linear layer in the deep learning sense. So we have a weight and we have a bias, and then I have some forward pass through this layer. So given a weight, just do a map model against it, add on the bias, and then the final thing we might wish to add, it's optional, it's to a way to initialize this. So by default, if I go back one, then we can initialize this just by passing in 2 values, the weight and the bias. We get default constructor. But we can also add an explicit init method, which does something slightly different. And so in this case, I've got a typo. That should be B key there, W key and B key in the 2 places. And so in this particular case, I take in 2 integers and I define my weight and my bias in terms of this. And so you can see that what we've ended up with here is a definition of this parameterized function, definition of a neural network layer. And the whole thing is hopefully pretty simple. It's designed to look actually a lot like PyTorch. The 2 points I guess I highlight here is that for those of you coming out of just general Python, this thing is a data class. You can see that with the weight and the bias things here. So this is Python standard library. And then for those of you with some background in JAX and know what I mean when I say it's a PyTree, then these things are PyTrees, linear. So instances of this linear class will be a PyTree. And for those of you who haven't seen that detail in JAX, all that means is that you can pass it across JIT and grad and things like that, and expect those transformations to go ahead and find your weight and your bias inside. These are types that JAX knows how to look inside of to go find these JAX arrays. So that's all that's describing. And so this is now just a really simple concept. This is how we represent our models. It has, as I say, a deliberately PyTorch-led syntax. It keeps the parameters in one place. It keeps the forward pass right next to it. And overall, the goal is that this is unfoot gunnable. This should just work. You just sit down and write it. something else I was going to touch on this point. Oh, right, yes, simply that if you do anything wrong, which is that we've done, I think, a pretty careful job of adding in like errors in every possible place you could possibly find. We've had people hit all kinds of like weird edge cases over the years, and every possible one is sort of walled off nicely if at all possible. And hence, I really like to say this thing is unforgettable and it just works. So I should probably have like a little GitHub star thing or something like this to sort of lend some credence to its popularity. So I think this is up to 2-point-something thousand GitHub stars at this point. So this is now one of the big model building libraries that we use in JAX, which is not bad for something that started as a PhD project several years ago and has since massively outgrown all of that. So let's take a look at some of the more advanced stuff. So this is where I've shown you sort of Equinox 101. This is how it's useful for building models. Let's also take a quick look at some of the more advanced stuff, as it says, for programming geeks. One of them, I am a big fan of using abstract base classes in nice ways. And so you can see an example here where our parameterized function is actually a differential equation solver. And differential equation solvers, well, they have some notion of a step. And then maybe we have a wrong recursive method for which we can define that step given some butcher tableau. And then maybe we have an actual concrete class down here at the bottom, which actually fills in that butcher tableau. And so there's lots of tools in here to support these kinds of abstract inheritance patterns, which I think are really, really nice for functional programming. Quick side note, this is not object-oriented programming because there's no mutation. This is a common mistake. So the goal here is to have a type system like Júlia with the safety of a language like Rust. Then meanwhile, speaking to people who are like auto-differentiation geeks, if there's any of you here, then we have some really cool stuff in here for things like treeverse, bounded while loop. This is UCLouvain style recursive checkpointing. But we've actually got extensions to this which handle things like online saving of checkpoints. And so for all like 2 of you who have heard of this and care, know that we have this. It's probably the single most complicated piece of code I've ever written. And it's the foundation of pretty much every iterative solver, like a differential equation solver, if you want to backpropagate through it. So this is very cool autodiff. And it's also asymptotically optimal as compared to more traditional gradient checkpointing. I'm guessing most people here have heard of gradient checkpointing, this idea of you lay down a checkpoint every root n steps. This is actually not asymptotically efficient. Log n is the best you can do here. And so this is actually what we do here. Okay, so that's the advanced stuff for the people who really want cool toys. Let's move on to take a look at another library. Don't worry, we're not going to just iterate through multiple libraries. We have other things to break this up. But first, what is this one other library? That is JAX Typing. So this is now probably my single most popular library. I don't know how many millions of downloads it gets every month, but it gets at least that many, which is pretty fun. And the use case that this is supporting, I'm guessing pretty much everyone here has probably written something that looks like this. They've said, okay, here's my function. It accepts 2 arrays. And then you've written a comment that looks like this. I'm willing to bet. And unsurprisingly, at some point, you have probably also passed in arrays which do not satisfy this constraint, and you have had bugs as a result. Probably this is an experience everyone here has had. And so correspondingly, how can we do better? It is to say, well, let's go ahead and import a couple of things like this. And now if I want to define, for example, a batch outer product, well, then I'm going to have some array X. So this is going to be a floating point array. It's going to have some number of batch dimensions and then this channel dimension. I'm going to have Y. We're going to insist that it's have the same batch dimensions as before and then have its own channel dimension. And then, well, it's an outer product. So what do I expect to get out of it? Well, I want all of those batch dimensions to be pushed on through. And then I'm going to have X against Y, so every possible pair. And then you go ahead and fill in your implementation. And so in doing so, we have now explicitly declared the D type and the shape of our arrays. And so this is, I think, a really, really useful tool for both just the human readability, just looking at this thing, but actually you can also arrange for this to be checked as you run your code and have a type checking error be thrown if what you're doing fails to meet these criteria. So again, this is, I think, a super useful tool for tracking what's going on as the shapes flow through your program. And then I guess one thing I'll also note here is that for those of you who are not successfully convinced by the end of this presentation and don't use JAX, this is actually still going to be useful to you because despite the name, which is now historical, this actually also supports NumPy and PyTorch and doesn't have a JAX dependency. The name is at this point just historical, so if you want to type PyTorch tensors and their shapes, for example, you can do that too. Okay, let's look at a little bit of a case study for putting these things together. So this is coming from the folks at Stanford. So they've written Levanta. And what is Levanta? It has a snazzy logo. And what it is a framework for training foundation models. So this is sort of like targeting ones around, let's say, the 20 billion parameter range. So, you know, you can go much larger than that these days, but this is already still pretty big. And what they're doing, they're scaling the logic of the model, scaling the logic of the model, the mathematics of it, from the logic of scaling the model. And so what does that look like? It means define your model in Equinox like you have been already. Go ahead and define some training step, and then you say, okay, here are my gradients. You can see I've done Joe's JAX.grad here in exactly the same way as I did before, not as a decorator, but just as an inline function. It doesn't matter, it's a function-to-function transformation either way. I get my gradients with respect to my model, and you write out the rest of your implementation. And then how does Levanta enter the picture? It is to say, well, great, let's say this is how I want to shard my data, my input data across my devices. How do I want to shard my parameters across my devices? And then with a couple lines of code, you can then split your model and your data in this way. So Levanta is a really nice framework for training specifically large language models. It's really written with that in mind. Here's like a little sort of picture to give you some sense of how your data and your models split across a grid of GPUs. And all of this, why am I showing this to you? Besides the fact that it's really cool and probably really useful to many of you in the audience, is that all of this is built on top of the libraries that you've just seen, things like Equinox, under the hood. And so this is, again, a very popular library. I'm not sure where they're up to now, but again, it's a nice example of all of this getting used in practice for you know, big, serious work. And then the two things they note here as sort of nice, sort of as like the difficult things that you probably couldn't do without it are things like bitwise reproducibility of your entire training, including if you get something like preemption. That's a really tough goal to meet. So this is really cool. And so with that, I think it's time to move on to part 3 of my talk. And so again, I'll just quickly pause. Do people want to jump in with any questions? I'm not hearing loads of people jumping in, so I'll take that as a good sign that I'm speaking sufficiently clearly, and I'll move on to part 3.
Maybe I have a question.
Go for it.
Yeah, could you please explain us like what would be the main advantages of Equinox, for example, against Flax or the other like?
Yeah, I mean, Flax is really the only other big one out there, so it's really Equinox versus Flax. And so I think I've actually got a whole page on this in the FAQ for Equinox. I invite you to sort of go poke at that in the documentation. But the short version really is that Equinox is just much, much simpler. Flax has had a long spotty history of inventing lots of new concepts, like custom scans, custom notions of variables. Its things generally aren't PyTrees. If you do inheritance, then things break in interesting ways. If you use bound methods, then things break in interesting ways. Basically, the story here was I started writing some of these scientific work that I'm about to present, found that I couldn't use Flax. It wasn't sufficiently flexible to handle these kinds of things that, like Flax can do neural networks, but it couldn't sort of handle these more general concepts. So Equinox actually arose originally as a way to represent parameterized functions more generally, rather than specifically neural networks. And then, of course, it just picked up neural networks. Equinox can just also do neural networks as a special case. I realize, obviously, you know, there's probably some, you would naturally accuse me of some bias here. You know, I'm advertising my thing. Yes, there's a competing thing. Obviously, my thing is better, right? And so I think for this one, I would just strongly encourage you, just go give both a try. I feel sufficiently confident that having tried both, you'll probably find yourself, I would give good odds of liking Equinox more. Give it a go and see what you think.
Okay. I think, yeah, I have played with Flax a little bit, but I haven't tried Equinox. But when I tried to move, I found like the syntax of both are somehow similar. Like it's the generating classes, generating neural network, specific architectures was not that different. So I didn't go to Equinox, but now I'll try now. Thank you.
You're very welcome. Yeah. Do just go give it a go. On to part 3 then, I guess. So scientific work. So diffracts, this is this first big one. This is actually where I started when I first started creating any of these libraries. This is the granddaddy of them all. What is this? This is differential equation solvers. This does a lot of new differential equation. What am I trying to say? It implements lots of differential equation solvers, and it actually has some new numerics going into it. And many of these new numerics are arising either out of the combination of some of its components, or out of the fact that we are writing it in something like JAX. And this really means that we can take advantage of first-class order differentiation to find these really clean APIs. So I'm going to give you an example of that now in my next code snippet. So let's go ahead, we'll import some things, and then what are we going to do? We're going to say, here is my ordinary differential equation, and I've not told you what it is, it's not important. For now, we just define some ordinary differential equation. And then I'm going to define a solver. And this is where things are cool, because what I've just written down here, I don't know how many people know Kverno 5 as a solver. This is an explicit singularly diagonal implicit Runge-Kutta method, which is quite a mouthful. But what it means is that this is an implicit differential equation solver. It's suitable for stiff problems. For such problems, you need to solve these sub-problems consisting of root-finding methods. How do you solve a root-finding method? You use Newton's method. How do you use Newton's method? Well, you need a Jacobian to do Jacobian inverses. If you look through something like, say, scipy.solve IVP, then you'll see that actually they take an argument. Jacobian equals something. You have to tell it the Jacobian so that it can evaluate this. But we're using JAX, we're not using scipy, and so this is one of those lovely things where we don't need to specify that anymore. I can give it a function, I can do jax.grad around it, and I get the Jacobian. This is super cool. And so as a result, we can define these kinds of solvers very easily. And so maybe now, given some initial condition, we start writing down things that look like this. So this is to say, please solve my ODE using this solver from 0 to 1 at time steps of 0.1 and some initial condition. And then obviously this is a very minimal example to fit in a small text box like that, but also, comma, you can add in loads of other arguments here, controlling things like step sizes or dense output or event handling or any other kind of weird differential equation thing that you want to support. We have quite a lot of them here. So as I say, this is really the granddaddy library of them all. And I think it's done very well for itself as well. So again, this is up to 1.8 thousand GitHub stars now, something like that. I'm taking a guess at a number. I need to go check. It's about there. Okay, now I don't want to just sit here. Oh, hello, go for it. I have a question.
Yeah, thank you, Patrick. Here. I have one quick question. So is this differential equation solve also remappable with respect to the initial?
Yes, it is.
Oh, I see. I should try. Thank you.
You're very welcome.
So
this is defined with that in mind.
Yeah. So Patrick, this is Raj. Just a question here on the diffracts. So this uses this adjoint method, right, while doing the backpropagation?
Oh gosh, I could go on about that a long time. Okay, so what do you mean when you say adjoint method? Let's be precise.
So like in typical neural ODE framework, they propose the adjoint method to do the backpropagation.
Okay. This is the whole spiel. Okay, I'll give you the short version. What people call the adjoint method is something which has varied over time. If you talk to people who've read some of the more recent literature, it refers to specifically the continuous adjoint method, solving this backwards ODE. And so that's come out of some of the recent neural ODE literature. But if you go and talk to, say, the numerical SDE people about a decade ago, then the adjoint method actually meant something different, which is to say, through the internals of the solver. If you then go and talk to the numerical ODE guys a decade before that, it meant something different again. It referred to, for example, how explicit Euler and implicit Euler relate to each other. They are in some sense an inverse. They work forwards and backwards. So the adjoint method is a piece of terminology I really strongly encourage people not to use. It is thoroughly confusing depending who you talk to and the context of it all. So I really encourage sort of being more precise, and in the case you're referring to, calling either optimize and discretize is best of all, or the continuous adjoint method. So that's big whinge number one. You've now you've really got me on this one, because this is also big whinge number two. We support this. It's called backsolve adjoint in our case, but it is a truly terrible idea. This is my time to tell you, please don't use the continuous adjoint method. Please just differentiate through the internals of the solver. Through the internals of the solver is the correct choice maybe 99% of the time, and even in the other 1% of the time is to go and use like a reversible, sort of commutative solver. Rather than the continuous adjoint method. I genuinely do not know of any reason to use this. Sorry, go on, you're about to say something. I'll let you say it.
No, that's correct. Actually, that explanation, that makes sense, because I use this PyTorch, the diffeq things, and they have that implementation of the adjoint method, but never knew that this is the way to go then. But that's good. Thank you very much.
Yes, you're very welcome. Yeah, I think the PyTorch implementation there is one that I actually wrote a lot of as well. So yes. I'm sort of partly guilty.
Yeah.
I think someone was about to jump in there. Maybe not. Okay. Yes, I mean, actually, do you know what? You're talking about PyTorch now. I think, I think we have that actually a comparison to that 2 slides from now. So it's timely that you mentioned that, and we'll get to that in a second. Anyway, moving on. Oh, actually, do you know what? What I might show off before we get to that, since you mentioned adjoint methods, let's jump back here. This while loop thing here, this thing, this is backprop through the solver. This is the correct way to differentiate through a differential equation solve. So, heads up. Okay, moving on. Diffract. Okay, now I'm not going to sit here and work through every possible library. There's like a lot of libraries out there, and you're all going to get very bored if I keep doing that. So I have one more slide where I'm just sort of like rapid fire. Look, we have linear solvers. Look, we have root finding methods and minimization and non-linear least squares and all that kind of stuff. Look, we have multiple dispatch. If there are Júlia people in the room, yes, we can do multiple dispatch in JAX as well. ... So we've got a few different libraries out there now. And rather than sort of, working our way through all of them exhaustively, I just want to note that yes, these things exist. Yes, they do all the things you kind of want them to do. And in many cases, actually, they also do some new numerics, where in the case of optimistics here, for example, we've actually defined a completely novel minimization strategy by taking the Hessian approximations of BFGS, combining with the classical trust region that you might see in something like Levenberg-Marquardt, and then also taking something like the sort of dogleg kink descents that you see in something like the dogleg method. And you can totally just weld these things together. Optimistics is very flexible. So there's some really fun toys hiding out in there for anyone who's a nonlinear root finding minimization, etc. kind of geek. Okay, rather than belaboring that point, we will now talk diffracts versus the everything else, because you've just highlighted some of this. Maybe it's worth me saying a little bit about this. So I started off by saying, what about diffracts versus SciPy? This is, I think, a really natural comparison. The way that I bill pretty much the entire JAX Scientific Ecosystem, the way I like to describe this is that it's auto-differentiable, GPU-capable SciPy. Everyone who's using SciPy, maybe you'd like to use this instead. Maybe you need GPU support. Maybe you need to backpropagate, whatever. And what are the differences? Well, first of all, we don't have a lot of the Python overhead that lives inside SciPy. SciPy, in particular, its differential equation solvers are Python and Fortran hybrids. The Fortran's pretty good, the Python isn't as much. And so in particular, overall, we're much, much faster thanks to JIT compilation. Obviously, there is this auto-differentiation and GPU support. And then also, we actually support just a lot more things at this point. SciPy's solve IVP is mostly just a wrapper around maybe sort of 5 different Fortran solvers, which are just like completely fixed to do exactly the things they do. Diffract supports a lot more things. So this has been super fun, I think, to build out. Now, there was this comparison that was just made, what about diffracts versus Torch DPQ? Which, yeah, I will note, this is a library which, gosh, it came out 7 years ago now, I think. I'm getting old. And the story here actually is that Ricky wrote the first version, and then a couple of years later I got involved in all of this and pretty much rewrote it from the ground up. But since then I've also obviously moved on. And so what's the difference? Well, first of all, we're much, much faster. One of these big limiting factors that PyTorch...
Patrick.
Go for it.
Sorry to interrupt. So one quick clarification. So
yeah.
Can you a little bit precise, how do you measure the fast Like how do you measure which one is faster than the other? Because sometimes I notice that JAX occupies more memories, but as a price for that, actually we get much faster computation, etc. So that I wonder, how do you measure the speed up and what others maybe? Thank you.
Okay, so I guess there's two things I should touch on here. There is, broadly speaking, the just forward pass through a differential equation solve. And then the other thing that matters for these kinds of differentiable problems is to do a forward followed by a backward pass. So in the case of that, something like SciPy, you can't differentiate it. So that's only the forward pass. And so in this case, I've got some benchmarks. I think they're in the Diffrax repo under benchmarks, where we do some of these comparisons. And there's some toy problems. I forget which problems it was now. I think in your ODE, maybe like a really small one, something like that. You can find similar examples as well against, I don't know, like the Robertson equation or something like that if you want a stiff problem. So the SciPy comparison here is a forward pass only one. For torch DFQ, how are these comparisons done? So there's two of them, two big ones we can do. So first of all, the forward pass. Again, this is where we really see big improvements. This sort of 200 times is coming from just the forward pass. And basically, this is, I think actually, this is a very expected sort of number to see, where usually compiled code, whether that's C or Rust or whatever, is usually about 100 times faster than Python. That's a sort of good rule of thumb to have in your head. And that's exactly the sort of order of magnitude that we're seeing here, which is basically just uncompiled Python, PyTorch code versus compiled C++ JAX code. Under the hood, JAX will trace your code with JAX.jit, and then this actually hits LLVM under the hood. And then also there is the backward pass. I've not touched on this here. For what it's worth, in the case of the backward pass, then the difference between the two narrows dramatically. JAX is maybe 1.5 times faster. It's much smaller. And the rationale for this basically is that now you have to worry about things like memory bandwidth. And so you are putting memory, maybe I've done this on both the CPU and the GPU. This is particularly noticeable in GPU, where you really care about your memory traffic. And for that, as a result, because you're pulling things out of your memory for the backward pass, which you've saved, you have to save results for your backward pass later, then we get different speed ups. Does that make sense?
Thank you so much. Yeah, it makes sense. Thank you.
Awesome. You're welcome. Okay, so yeah, Diffrax versus Torch DFQ, as I've already said, is much faster. This is basically just PyTorch versus Python versus compiled code. We have a lot more features. I think PyTorch Torch DFQ, was really cool when it first came out, and then since then, we've just gone ahead and just built out loads more things on top of it. And then I don't know if we have any Júlia people in the room, but if you do, then probably you are champing at the bit to be like, what about differential equations.jl? What about the whole Julia scientific ecosystem? How does all of this compare? I mean, first of all, obviously it's a different language for people. For those of you who are familiar with Python, maybe prefer something like Diffrax. If you don't, that's fine. I think probably the big thing that we've got going for us over in the JAX ecosystem is this rock-solid auto-differentiation system, and likewise rock-solid auto-parallelism system. So if you want to run your differential equation solves against on your cluster of 32 GPUs, that's the auto-parallel, you can totally just do that. It just works. It's very easy. In contrast, Júlia has largely focused on sort of smaller problems, and in particular, it doesn't do as well on things like SIMD and things like that for these kinds of big GPU problems. And then meanwhile, auto, again, anyone who's, sorry, go for it.
Yeah, can you talk a little bit more about this auto-parallel? I mainly work, first, I'm not that much familiar into this part of programming things. I'm just more like run my codes and things like that. And I mainly use JAX. I really like it. But for example, one thing that I found a bit complicated in JAX is when you want to do multiple GPUs. In some sense, like for example, PyTorch, and I'm not sure if TensorFlow, but for example, in PyTorch, there are some options that you just specify the number of devices and then the code does everything. But maybe I didn't look in the right place, but I didn't find a place where I could do something similar with.
Yeah. So this is one where in particular, this case of multiple GPUs is one which I think is very strongly in JAX's favor. This is one of these ones which just does incredibly well. If I go all the way back to this JAX introduction, here we go. Yeah, it's this part here. So if I just write, call my jitted function on some model and some data, that'll just work. This is just on my laptop. And then with basically just those 2 lines of code, which is to say, please put my model on all of my GPUs, and please split my data into 32 fractions of my data, 1 on each GPU. It just takes a couple lines to do that. And then you just call your function in exactly the same way. This is, I think, so the 2 big talking points here is that JAX's model for this is write one big function, compute loss in this case, this cloud of compute loss, and this then been jittered. To write this one big function as if you were targeting this one gigantic machine, or if you like, you're writing out just the mathematics and nothing else. And you don't have to think about the details, the compiler will figure it out for you. And what's going on there is this is sort of big talking point number 2, is that this is sometimes referred to as the compute follows data parallelism paradigm. Where you define where your data lives, your model and your x and your y, and given that your compute loss function, this is then automatically split across all of your GPUs or whatever else.
Yeah. So when I do this device put GPUs, the x and y already gets like in this kind of like GPU batch groups, because I remember that I was trying to play with the documentation of, for example, with PMAP, and for example for PMAP you had to make sure that your arrays had to some specific structures to be able to use PMAP. And
yeah, so I would say PMAP is now several years old. That used to be the way it was done very, very long time ago. And then since then it's just write JIT and it just works, is I think the short answer.
Okay. And then the model automatically defines how many GPUs I have available, or like how many, and the partitions and everything takes care of everything.
Sorry, say that again.
So I assume that in GPUs will be a list of the name of the devices that I have, right?
Yes.
Like
yes.
Okay, so then this device put will make sure, okay, that all my partitions are in the right way to, and also then you have like there are many ways to do parallelization neural networks, right? Like then how would the model choose which one is going to use? Like,
yeah. So when you talk about different ways of doing parallelism, this is probably you're thinking of something like data parallelism versus like FSDP or anything else. And basically, most of these are defined by where your data lives. And so a lot of these, for example, maybe you replicate your model onto every device. So this is data parallelism, as you're seeing here. But maybe you also just put like a part of your model on every device, and then send them back and forth, send those weights back and forth between each of your devices as each device needs it. And so because of the fact that these strategies are defined by where these arrays live, then given that information, the compiler can then produce some communication strategies to move this all around. As a practical matter, it really seems to do incredibly well. This is very much the standard way of doing this. It's very unusual for people to want to customize that. Although if you really, really need to, JAX offers some lower level APIs to do so.
Okay, got it. Thank you.
Cool, you're welcome. I think maybe the other thing I should highlight here, take a look at the Equinox documentation. There is an example in there walking you through exactly this to run things on, I think it's 8 GPUs. And so that sort of walks you through, oh, look, it walks you through the same story of, oh, look, it's so simple.
Okay, so in Equinox, I'll look for it. Thank you so much. It's been really helpful.
You're welcome. Let's move on back. Yes, okay, so we said this was all based around this point about autoparallelism. So yes, JAX does autoparallelism very, very well. And then the other thing I was going to touch on in terms of Júlia is, and as I think somewhat infamously now, Júlia has yet to really get a strong auto-differentiation system going. It's got a dozen different ones doing slightly different things. And again, JAX is just one out much more strongly here. And both of these points, by the way, this is not Diffrax. Diffrax did nothing for that. That is purely just coming from JAX doing a good job. We both get the same speed because basically they're both just compiled. In fact, I think both of them compile to LLVM under the hood. So unsurprisingly, they both do very well in this regard. Let me go back 1 point. There we go. And so this is like my quick summary slide of why Diffrax. Why is it really cool as compared to some of the other options out there? These are obviously the big 3 famous ones. I would like to highlight that I don't have it out for any of these other options. I have at various points in my career used all 3 of them. And diffract was really born out of a need for some intersection of the things that didn't previously exist. So, okay, fine, I'll sit down and I'll write it myself. And so that's kind of the story here. But, for people who are already using one of these three, go for it, keep using it. If it works for you, it still works. Maybe give diffract a try for your next project. I'm not going to advocate rewriting your current one. Okay, so now let's look at a very real case study. So this is not me just like talking about how does this compare, but this is a really fun one which may speak to some of the physicists in the audience. Where what have we got here? We have two black holes orbiting around each other. And then as they orbit, they spin down and they get closer and closer and closer until eventually they merge in this incredibly sort of like gravitationally catastrophic events. And so you can see you get this strain, as it's written here. You can see it sort of wobbles back and forth with increasing severity right up until the point of the merger. Now, this is an incredibly computationally expensive thing to model. You get some pretty pictures like this coming out of it. You can see our two black holes orbiting one another. And then one of the really nice examples of kind of all of the JAX ecosystem and how it's been useful for these guys is how they get their ensemble of GPUs and then what they've been finding as compared to their best possible NumPy implementation, I think this was, that they saw a 100 to 500 times speed up on an A100 and a 200 to 2,000 times speed up on a H100. And a lot of this is just coming down to JAX supporting GPUs and JAX just being efficient with its compilation strategy. They were using Lineax. I touched on this earlier, so they got some high-performance splines coming out of this. And then I got this lovely quote from Casey, which is I think really sort of justifies a lot of this, was how their non-JAX version takes 2 hours to 10 days, but with the JAX code, they get results in minutes. And so, like as a library author, like why do I do any of this? Like this is why I do any of this, because I hear these kinds of stories and I think it's amazing, and I love being able to support the scientific endeavor in this kind of way. And then this brings us to our final case study for today. And I'll close the presentation not too long after this. So our final case study is we're actually going to go ahead and we're gonna set up a very small neural ODE using 3 of the libraries that we've seen today: Equinox for models, diffracts for differential equations, and JAX typing for representing the shapes and d-types of arrays. So what does that look like? Something like this. We're going to go ahead, we'll import these libraries that we've seen. We're going to define our neural network. Equinox ships with equinox.nn dot a bunch of standard layers. So there's equinox.nn.linear.con for convolutions, etc., etc. And then also in particular we have MLP, multi-layer perceptron. So we can go ahead and we can define a small multi-layer perceptron here. So I think in this case we've got one hidden layer. So we like input layer, hidden layer, output layer. Key here, for those of you who haven't seen this, JAX does explicit randomness rather than having this sort of secret stateful PRNG in the background. This is one of JAX's superpowers. This is how, for example, earlier Levanter was able to get bitwise reproducibility. You get these kinds of things when you have these explicit handling of randomness. So here's our neural network. Let's go ahead and solve a neural ODE. Our neural ODE will have some initial condition, y0. It will be a vector of size 4. We'll solve our differential equation. And so what have I done here? Gosh, that's rather a lot of code all at once. Well, okay, we've got lambda, TYR, so MLP. So we're solving an ODE given by dy dt equals that MLP. That's what that ODE term is telling us. It's an ODE whose right-hand side is this neural network. We're going to use SIT5 to specify 4. So this is now probably like the standard default ODE solver. You often still see DOPRI5 sometimes in places, Dominant Prince 5.4, but these days SIT5 is generally reckoned as being slightly more efficient, so it's a better default choice. So we'll solve this from 0 to 1. We'll solve it in step sizes of 0.1 from this initial condition. Our output, we're going to say, please give me an output at 10 linearly spaced time points. So this is exactly like numpy.linspace. In this case, we just have jax.numpy.linspace, and so we're going to linearly space 10 output points from 0 to 1. And so correspondingly, we'll get 10 copies of our state out. That's what we're going to return here. And you can see this now actually in the return type annotation up here. So our input was a vector of size 4. So our output now is 10 of those stacked together. It's a matrix 10 by 4. And so this is what solving a little neural ODE looks like by just bringing all these pieces together. one of the things I do quite like about this story is the extent to which we can take neural networks and we can jam them inside differential equations, and this just works. And the reason that this just works is because a neural network is just a bunch of addition, multiplication, whatever else. And the numerical differential equation solvers are also just a bunch of addition and multiplication and whatever else. And so you can just compose the two. And what you end up with is just this big auto-differentiable computation graph. And so again, just like auto differentiation, auto parallelism, and all these fun things do just work. This is just one big computation graph to make that happen. So with that brings us, I think, to the close of this presentation. These are the 3 sections that we've seen. So I think this is my final slide. If you're interested in the JAX Scientific Ecosystem, I guess I should clarify, people have done other things not discussed in this presentation. But if you want to see the JAX Scientific Ecosystem, a lot of this you can find starting off with Equinox and then just sort of following all of the links in the README. If you want to come and say hi to me, then please feel free to come and reach out anywhere on the internet. I'm currently working at a startup, Cradle.bio. I get the sense this audience is maybe more sort of like physicists and engineers, but if we do have anybody interested in doing biology, we are a startup full of ex-physicists who decided to come and do protein language models. And so we're now a Series B startup, about 50 people, more customers than I frankly have time to deal with. It's going very well. If anyone is interested in talking biology, please feel free to come talk to me. And so all that means to say is thank you very much for your attention. You've been a wonderful audience, and I'll take any further questions.
Thank you so much for your great talk. So now we open the floor for questions. Do we have any questions for the speaker?
First of all,
Yes.
let me start. So thanks very much for what a wonderful talk. I really enjoyed it. So maybe this might be a general question. I also get from even students or colleagues saying that why JAX? Then in the level of considering there's some preliminary knowledge on how things working, I can literally show, like, see this comparison web page that 100 multiple times faster than the others, but maybe can you a little bit address on those points? People probably you may get those questions a lot, PyTorch versus the JAX. Then I personally like JAX because the way it is written is more familiar with me, like, you know, MATLAB type coding style. But I don't really get to the point to give a simple and convincing answer to that. So I wonder if you may have one.
Yeah, how would I describe this comparison? So I think if you're doing anything to do with differential equations or classical scientific modeling, anything like that, then JAX is much, much better just because it has a much better compiler and it's much faster. It supports forward mode auto differentiation. It supports VMAP in far more general ways than Torch.vmap. Torch.vmap is not good. And so for anything of that nature, JAX just has more things and is faster, so it's clearly a better choice. I will offer, however, the opposite caveat that if you are just training a big neural network to do supervised learning, and maybe that's it, then it doesn't matter, pick whichever. That for simpler tasks like that, then either's fine. I think that's my like 10-second summary. I think maybe the other thing I will highlight is for anyone who's coming out of a more of a mathematical background, or more like a theoretical CS background, so I don't know, functional programming and type theory, those are the kinds of words that make you very excited, then JAX, and actually also Equinox on top of it, has done a lot of work to support that style of programming. So that you get things like the explicit randomness or these program-to-program transformations, nice composability, all this kind of stuff, which you don't find in PyTorch, which in contrast is object-oriented. And of course, for many people these days, object-oriented, kind of a dirty word. And so if you are sufficiently a programming geek to care about any of those things, then this is also one of the big reasons to prefer JAX.
Thanks so much. Can I ask one more question?
Okay. Yeah.
So I wonder, Equinox has equipped with certain built-in functions that handle some stochastic computation, like dropouts or variation autoencoder. You gotta plug some new random variables every iteration. So does it comes with the Equinox?
Yep. Yeah, or in some cases just in JAX, because JAX already ships with random sampling from various probability distributions. But stuff like dropout, for example, that's an Equinox.
Gotcha. Maybe my last question is there any like tip or trick that maybe reduce the memory capacity required by JAX? Some cases it simply takes a lot of memory so that
yeah, if I had to guess, what you're probably looking at here is that JAX actually pre-allocates memory, in particular on your GPU, in order to reduce the amount of fragmentation when it allocates later. And if you don't want that, you can turn it off or you can change the fraction. So if you take a look in the JAX documentation, you'll see somewhere something there about controlling the memory. It's very likely that you're just looking at the default behavior, but you can change that if you wish to.
Oh, I see. That's all. Thank you so much for a wonderful talk.
You're very welcome. Any other questions?
Hello. Hi.
Hello.
Hi, this is Chen from Brown University. So I'm heavily using Equinox in my daily research. So I do like that package. But I encounter a small problem that when I use the pure JAX manipulating with the array and taking the automatic differentiation, it seems like that is slightly faster. Well, not very slightly. I mean, it's like the Equinox version takes me like 30% more time. So do you have any idea how to especially improve the performance with these filter operations, like the filter JVP or somehow like that? Because in these, well, we guess that in these operations take much more time than compared to the pure JAX implementation.
Have you compared, have you identified that it is because of something like a filter transformation? Like, is it literally the exact same JAXPR under the hood? Or have you changed
we guess that's some sort of due to the filter JVP operation. Since after we remove these parts, it seems like the speed is accelerated a lot. So I guess that maybe, Raj also talked to me with these things. So we guess there may be filter things didn't cache something. So I'm just wondering if there is an approach to improve this.
Yeah, so the comments I'll make here is that since Equinox lowers to JAX under the hood, well, not lowers, but like is JAX, and there is the JAX.jit compiler within which whatever you write kind of doesn't matter, it'll all get JIT compiled away, then typically you should find that anything you write in Equinox is just the exact same speed as JAX. And if that's not the case, then probably it's been written wrong somewhere, or there's been written differently, I guess. In terms of like what are the common reasons for doing something differently? One of them is simply that you've written slightly different computation graphs for whatever reason. Go ahead and run something like jax.make.jaxper and just take a look. Like, is what's being compiled actually genuinely the same thing in both cases? Number two, another frequent issue which some people sometimes run into is that they are accidentally recompiling with jax.jit. And so if you want to check that that's not the case, then there is equinox.debug.assert max traces, I think it's called. And so you can use that to assert that you aren't recompiling accidentally, which again is a sort of common gotcha. And then the, I think third one, which you've touched on, is in this possibility that some of these filtered operations are adding extra overhead. If they are inside of the JITted region, then they can't, because that gets JIT compiled away. If they are outside of the JITted region, for example, equinox.filterjit itself, then this is conceivably possible, but in practice, we've benchmarked this and it adds maybe microseconds of overhead. And so if that's adding a lot of overhead, then, I mean, A, I'm surprised, but also B, there's also in the Equinox documentation, there's an example for its low overhead training loops, where maybe take a look at that as a way to finesse this problem sometimes. That's a very unusual scenario to be in, but you can take a look at that.
I see. Thank you very much. Also, by the way, we are currently conducting some research about the large language model. So I'm wondering if there's anything like the transformers for Hugging Face, like the alternatives in the JAX, because we have a lot of historical code in the JAX. So we do not want to move them all to the PyTorch version. It would be better to have these things.
Yeah, I would love it if someone I would love it if that existed. I don't know of an equivalent to Hugging Face transformers in the JAX ecosystem. People are writing loads and loads of transformers in JAX, unsurprisingly, but people haven't like standardized them into one library in the same way. I think perhaps what I'm hearing here is an opportunity. If perhaps you'd be interested in starting your own open source ecosystem, little mini empire.
Well, great. Thank you so much for that.
You're very welcome.
Next.
Thank you so much. So I got one question. Is there any equivalent framework as PyTorch Lightning for JAX?
So you will find some of them out there. I'm trying to remember what they are now because I don't use any of them myself. If you go searching through like JAX ecosystem links, then you'll find some. They do exist. But for what it's worth, when I write PyTorch, I don't use Lightning, and when I use JAX, I have no desire for an equivalent. My general feeling is that like these things are for training loops, and a training loop is a for loop. I'm quite capable of just writing out a for loop. Whenever I've tried something like Lightning, I've always found it is insufficiently expressive at the end of the day for some detail I need later on. And I generally would encourage people to just write out those for loops themselves. I think it ends up giving much more flexibility at very low cost.
Thank you so much. Do we have any other questions for the speaker?
Yeah, maybe I
Yes.
have one more question. Again, thank you so much, Patrick, for your help before. I saw that before you had like in one of your slides you have something like optimizers, and it was like OPTX, and that brings a question that there are a lot of optimization libraries in JAX. You have JAX OPT, you have Optex, and now Cities Optimistic. Do you have any specific preference to some of those? I'm asking that because maybe when I started using JAX, it was when one of the previous versions, and for example, I think that I was using JAX OPT, if I'm not wrong, and I remember the LBFGS implementation was not working as well as expected.
Yes.
Yeah, I had the same problem. Yeah.
There's a story here. So indeed, JAX Opt is one of these very early optimization libraries in JAX. It, as you note, didn't work very well. Optimistics was actually born out of my own frustration of not being able to use this to do what I wanted to do. So I wrote my own. In fact, at this point, actually, the story has come full circle. The JAX Opt people have actually said, you know what, let's not bother, because Optimistics or Optax actually do it better. So at this point, JAX Opt is deprecated. Then in terms of Optimistics and Optax, so these are now the two big ones. These are, I think, both of them very good at what they do. And the difference is really that Optax is, this is a library from DeepMind. This is for first order gradient methods. So, you know, Adam, SGD, this kind of stuff. Optimistics, if you like, is for everything else. And so we don't really try to implement gradient descent. We don't try to implement Adam or whatever. Optax has already done that very, very well. We are there to implement things like BFGS and Levenberg Marquardt and this kind of thing instead. Any other questions?
Juan, your mic is off.
Oh, sorry about that. Yeah, thank you. And one question, in one of these two libraries that you mentioned, do you know if they have like a BFGS implementation, and how flexible is to modify? Because, for example, if you go to the SciPy implementation, it's kind of straightforward, and it's kind of friendly enough that you can just put more lines and then everything turns out fine. But sometimes I find that when you try to play too much with the JAX, maybe it's because, as I said, like I write neural networks. I'm not like a software development, and that's not my strength. But sometimes I found that it's not that easy because you modify something and then you get like $100 and then it's a bit frustrating.
To speak to these points, yes, Optimistic includes a BFGS implementation. In fact, you can see the letters BFGS there. So there is a direct optax.bfgs, but we also have a slightly more abstract version of it for those who want to play around customizing things. So that's there. If you want to be able to write your own or customize things, this is actually one of the big things I care a lot about actually in developing a lot of this ecosystem, where one of the common threads you'll notice actually throughout this entire talk is how what I've written here is my class defining an optimizer, and then I pass in an instance of that class to my solver. If you look at Lineax, you see the same thing. My QR solver, I pass in an instance of that to the linear solve operation. If I go take a look at diffrax, you see the same thing. Here's an instance of my solver, and I pass that into my diffx solve operation. And so throughout all of this, what this is saying, what this is meaning, is that if you want to define your own solver, you can. Just go ahead and write one with the right API, with the right methods, and pass it in, and it will just work. And so the whole ecosystem is designed with this kind of extensibility in mind. And so this you should find that that's very easy to do, either just by completely writing something from scratch, or if you like, copy paste what's already there and make your changes. This was really important to me when I made all this.
Okay, that's really helpful. Thank you so much.
You're welcome.
Yeah, thank you so much. And I think Professor,
I had a non-technical question, very elementary actually. In terms of, okay, because a couple of years ago when I was trying to, I have an M1 on Mac right here. It was hard to install even PyTorch and TensorFlow. And I had to look at a lot of videos and then figure out, okay, what to do. And, like it was a tedious process, right? All the things have improved by now. So is JAX easy to install? Just using or Brew or whatever, right?
Yeah, I use JAX all the time on my Mac as well. That's what I'm sat here using at the moment, and it does just work. This is typically pip install JAX in terms of making that work. I will note that this is all just using the sort of like standard CPU implementation, so it's not trying to use the metal backend, and I think that's totally fine. There is a metal backend. It's maintained by Apple. It doesn't seem to work very well. But just use the one that JAX ships with by default rather than this extra plugin, and you'll be fine.
So also, your Mac is M1?
M2, I think, but don't quote me. I'll need to check.
Yeah. Okay. Okay. Thanks.
You're welcome.
I played with this plugin that you mentioned in the M. I also have an M2, but it works if you're. For example, you're training like normal neural network supervised learning, it works. But if you try to do recursion, for example, we work a lot with physics-informed neural networks where you have to get derivatives of the output respect to the input. And then it doesn't work because it's explicitly said that operation is not supported. Like obtaining like du dx is not supported in Mac.
Yeah, so to be clear there, you can use JAX on a Mac, just use the default CPU implementation and not the metal backend that Apple has created. But yeah, okay, thank you. That's good. It's good to know that the metal backend still needs some work. Any other questions? Silence.
Do we have any other question? Yeah, I think we don't have any other questions.
Well, that's pretty good anyway, because we're right on time, actually.
Yeah, thank you so much for your great talk.
You're very welcome.
And thank you for joining us today. So I think it's time to close the session. I hope everybody has a great weekend ahead. Bye.